Okay, hey friends. We are going to talk about projectile motion. So we've been talking about things falling and speeding up due to gravity. Now what happens if we're launching something and working in 2 dimensions? So at this point you should have watched the video that was explaining your pivot lab. And that's from Mr. Mark. He talks about how velocity in the x direction is constant. There's nothing to slow it down or speeding up once we've been launched or kicked or rolled. And so we can think about the x direction as constant velocity, which has its own set of equations. And then in the y direction, it's the same as if only acceleration was working on it, acceleration due to gravity. And so the object's going to speed up just like it would if we dropped it. And so in the y direction, we can consider only constant acceleration, where acceleration is due to gravity. If we put those together, we can get projectile motion. So how do we actually look at these? How would we go about solving a problem? Let's look at a couple of things first. Maybe if it will project. Here we go. The best way when we organize our page is to split it into x and y. Keeping track of these two pieces separately lets us know exactly what's going on in the x direction and in the y direction. And if we know that this object is falling, moving constantly, having a constant velocity in the x direction and constant acceleration in the y direction, the time is going to be the same. And so if we have enough variables on one side, we can solve for a time and use that to find whatever we need on the other side. And so we're going to use these together, even though they're very separate. All right, so there's 3 kinds of projectile motion problems. The first one is an object is being thrown horizontally off of a cliff or a table or something. We might also see the word rolls off the table. That's to indicate that it's just going straight off the table. It's not being launched at an angle. And that has its own unique kind of set of known and given values that we have to deduce from that. The other type is an object is thrown or launched at an angle off of some height. So it's going to travel upwards for a bit before it starts coming down as it's moving also in the x direction. And then the third type of problem we see is an object is thrown or launched at an angle and returns back to the same height. So I kick a soccer ball, kick a football, throw a baseball. The height isn't changing. All right, so there are some things we know, and this is kind of a little bit overwhelming. There's not really a good way to throw this out. So let's just look at the horizontal motion first. Well, we know if it's only moving in the x direction, the value of the velocity is only going to be the x velocity. The initial value of the velocity in the y direction is going to be 0 because it's not moving up or down yet at just that instant. It's very similar to if we were to drop an object, except now we're also moving in the x direction. We also know that acceleration is going to be 9.8 meters per second squared downward. And so we have a couple values that we can use right off the bat. So let's look at that. If I have a beach ball and it's thrown horizontally with a velocity of 3.6 meters per second off of a 15-meter tall cliff, how far does it land from the base of the cliff? So this is a lot of translation. I'm going to start on my paper first by separating it into x and y. So what is happening in the horizontal? Well, we know this is constant velocity, so there are only 3 variables that I have to keep track of. Velocity in the x direction, displacement in the x direction, and time. In the y direction, I have my displacement in the y direction, the height of the cliff. I have an initial velocity in the y direction, and this is where subscripts are really going to come in handy. I have a final velocity in the y direction, an acceleration, and a time. So the easy one for all of these, as long as we're on Earth, our acceleration due to gravity is 9.8 meters per second squared. Boom, done. Okay, let's talk about reference frame for a second. I'm just going to say down is negative because that's the way you guys tend to go. Remember, that choice is yours. It doesn't matter if you choose negative or positive, but then everything has to match. So we know that acceleration is always going down towards Earth. So it's going to be a negative 9.8 based on my negative reference frame. We also should talk about, well, we're moving in the x direction now, and so we need a reference frame that also deals with left and right. And so I'm going to say right is positive. And so in my reference frame over here, I'm going to indicate that left is negative and down is negative. Okay, so what else do we know from this? Well, we see the words thrown horizontally. That's to remind us that in the x direction, the velocity is 3.6 meters per second. So whenever we see this idea of something being thrown horizontally, we know that our initial velocity in the y direction is 0, and it's only moving in the x direction at the beginning. So this, if you notice, is a lot like an object being dropped from some height, except now it also has an x velocity, and so it's going to follow a horizontal path as well. I'm falling from a 15-meter tall cliff, and so my displacement is going to be 15 meters. I'm going down, right? If I put my finger on the start, I'm falling down, so my displacement is going to be negative 15. And then, woohoo, I have 3 things on the y side. And so I can use my equations there to solve for what I need to solve for. And let's look. It says, how far does it land from the base of the cliff? So that's asking in a horizontal direction, how far does it go? And so we're looking for an x displacement. I know these two are always going to be connected by time. If I can solve for time over here, I can use it over here to solve for displacement. So I have 3 equations that I use for constant velocity. Remember, they look like this. Plus 1/2 at squared. And we have to be careful now because we're talking about only in the y direction. Vy squared, Vy squared plus 2 times a times delta y. Okay, can you see all those? Just barely. All right, so which one is going to help us solve for time? Well, if we look here, our initial velocity is 0. We have a displacement of a negative 15, an acceleration of negative 9.8. I'm going to go with this one. We're not going to have to use the quadratic because this value is going to be 0. And so I'm going to start off with the equation in variables. And then I'm going to plug in what I know. Negative 15 is equal to 0 times t, which is just 0, plus 1/2 times a negative 9.8 t squared. I have to get my calculator out here. I know a negative 15 is equal to a negative 4.9 t squared. I'm going to divide each side by a negative 4.9. And I get t squared is equal to 3.06, and if I take the square root of both of those, I get a time of 1.75 seconds. Got it. Okay, but I'm not done yet because I'm trying to find a displacement in the x direction, how far from the base of the cliff it's landing. I know this time is 1.75, and I know there's only one equation that I have to keep track of for constant velocity, and that's my velocity is equal to a displacement over time. Right? There's no acceleration, so I don't have to use these 3 variables or 3 equations over here. So I'm going to plug in what I know. I know this is 3.6. I know the time is 1.75. I'm going to do a little algebra and multiply each side by 1.75. And I'm going to find my displacement isn't very far, because I'm not launching it very fast. 6.3 meters. And there she is. Woohoo!